Welcome back to this coding session today. Last time we coded a simple ball animation like that, which applies gravity to a ball. But I would like to extend this to a, multi-body simulation, just like planets in space, and they attract each other through gravity. And for that, I have already created a new repository. I have copied the old source files over and removed all of the unnecessary stuff. And right now we have a struct circle that contains coordinates x, y, a circle has a radius, a vx and vy, which are the velocities in x and y direction. And I would say we should extend the circle. Actually, circle is not really a proper term now. It should be something like body or planet or mass or object, but let's keep it like that. And each circle should have a mass, because depending on its mass, it should attract other bodies. Then there's a function fill circle. We have coded this together in one of the last episodes, which is just a function to draw a circle onto the surface. And it's very simple. So we just check the circle's coordinates, x and y. And based on the radius, we check which pixels are inside the radius and which aren't. And the pixels inside the radius, they are colored white. So here is the coordinate within the circle. So we check the radius, and then we draw the pixel according to a set color. Then we have a step function for the simulation. So we increment the x coordinate of the circle by vx, we increment the y coordinate by vy, the x and y speeds, and we also increment the vy, the y direction velocity, according to gravity. And now here's the interesting part. So far, our small little program mimics the behavior of an object on Earth. So the object's own mass is not really accounted for, and we just assume that gravity pulls the object downwards. But now we have to generalize this problem. First of all, we have to add a second circle. So we create another circle. Maybe we will make this an array later. And the other circle has the same radius, but not the same x and y coordinates. Let me just say x is whatever, 400, 400, come on, 400, y is 400 as well. Then the radius, which is that number, is still the same. Oh wait, no, let's make it smaller. Let's make it 30. And the x speed is going in the opposite direction, and it's a bit different, and the y speed is also going in the opposite direction. So let's have a look at how that simulation looks like now. So we still have just one ball. Yeah, obviously, because we haven't rendered the circle onto the screen yet. And we can do that down here. And let's call a second fill circle method. Let's fill circle 2. Do we use color white? Yes, let's use color white as well. And that's the second circle. It doesn't move for whatever reason. Why doesn't it move? Fill circle, circle 2. Ah, of course. Yeah, I know why. Because we also have to perform the step function for circle 2. So the step function is what calculates the new position, the new speed, applies gravity and all that stuff. So now we have two balls, which is already a good thing. They don't collide. I'm not sure if we will implement collision detection in this episode, because I want the two balls to rotate around each other as in a two-body system anyways. So let's change gravity, or let's remove gravity entirely. And now the balls should be just floating around, getting smaller and getting slower and slower on each collision with the borders, because the borders are dampening. That is fine. Maybe we will reduce the dampening a bit. In space there's not that much dampening. Let's make it 0.95, 98. Let's see how that behaves. Yeah, they are quite fast. And because the simulation is going so fast, we also have to refine the step function a bit. So the x-coordinate of a circle, it increments by Vx multiplied by delta time. So now we define the time frame over which we simulate. Okay, but we don't have a delta time yet. So maybe let's make this a global constant, delta t. It will not vary anyways, because we're going to simulate fixed time steps. And we're going to, let's just make the 0.1 and see how it looks like. Okay, and now the circles are moving much slower, as you can see, and much smoother, which is a good thing. And now comes the interesting part. We have to somehow apply gravity. But how do we do that? Because right here, the entire step function is laid out in a way such that the circles only account for their own acceleration and velocity and position. But now that should be dependent on the other circle as well. So should we maybe introduce a second circle here? Circle, let's do that. And when we generalize the problem, we can extend this to an array maybe, so that we have an n-body problem. How do we calculate the new position? Yeah, we now have two circles. The x-coordinate and y-coordinate, they update according to velocities. That is fine. That's completely fine. But the acceleration of those circles updates according to the other circle. Oof. Okay, let's create a new section in this routine here. Update gravitational acceleration. Okay, and to do that we have to know the distance between the circles. Distance squared is equal to the circle. Okay, circle x coordinate minus the second circle x coordinate multiplied by itself. Maybe we should use the math functions here. Yeah, I'm not going to do that. Wait. I'm going to include math.h and here we are going to let's calculate the distance, not the distance squared, distance, and then there should be a function. Oh, of course have to say that this is a double. And then there should be some function that says some power or something like that. Square? Is there squared? Squared. Square root. We are going to need the square root of circle x minus circle 2x. And then here we have to calculate the power of that. So the power is going to be C math functions power. Oh, there is a power function apparently. Why didn't it show up in my linter suggestions? So there's pow base power. Okay, pow. That's the base, and the power is 2. Yeah. Multiplied. No, we don't need multiplied. We need a plus. And then we need the difference between the y coordinates as well. So that's going to be circle y minus circle 2y. And then the power of that, pow, to the power of 2 square root. Okay, so that's the distance. Let me just check if it compiles. Of course it doesn't compile. Ah yeah, because I used the step function wrongly. So here we do a step on circle and circle 2. That should work. No, it doesn't. It doesn't work like that. I need to pass the address of circle 2. And then in the step function, wait, let me compile it, but one of the circles won't move because in the step function we only consider one circle still. Okay, there's still an error. I think I have to somehow link the math library. How do I link the math library? C link math library. I never know how to link libraries. So please, if you have some tip for me, then just write it in the comments, please. So I know I see a library that I want to use, for example, math.h. How do I know how I link it? Never know it. Okay, in this case I can append -lm. I will just do that. -lm, and does it compile? No, not yet. Of course, I have not appended it to the compilation command. Yeah, so that works as expected, but that doesn't work with any library. So yeah. So now we have the animation and only one circle is moving. Well, because according to the distance, we now have to apply a gravitational force. And the gravitational force is, let's call it a gravity. Acceleration gravity is proportionate to 1 divided by distance squared. It should be distance squared. So let's do power of distance 2. Let's see, just if it compiles. Yes, it does compile. That's good. And now we have to apply that gravitational force according to, let me draw that for you in Paint. So here's a nice instance of Paint that we have, sorry, one circle, the other one. And then I want this circle to go this direction. Come on. there's a nice brush. So I want this circle to be pulled in this direction and this circle to be pulled in this direction. To do that, we can probably somehow, based off the center points of both circles, calculate this, the vector that links both of those circles together. So there must be some line here. How do we do it? Yeah, the gravity vector for circle 1 is just, yeah, this point right here, point of circle 2, minus point of circle 1, and that is then the vector in that direction. Let's just implement that. Okay, we have a gravity. Now, let's create, I think the vector, yeah, consists of two components. So we're just going to create the A in direction X for circle 1, and that is going to be, oh, I really don't like that notation, AX1. Okay, let's just do AX. AX is going to be circle 1 dot X minus circle 2 X minus circle 1X, and double AY is going to be circle 2 Y minus circle Y. Those are the vector components. And I think now we can apply these forces or accelerations. Let's just do circle. The first circle's speed, Vx, is going to be incremented by Ax. The same goes for the first circle's, oh, typo alarm. Vy is going to be incremented by Ay, and we can probably copy that for circle 2, only that the speeds are going to be decremented. Well, let's just do incremented by the negative force, because from the other circle's point of view, let's just pick pink here. From this circle's point of view, the vector is pointing in exactly the opposite direction. And of course, I think I'm missing something. Here the force, the acceleration is increasing with distance, but we don't want that. We want to normalize this vector and then apply this gravity constant. So let's divide. No, how do we do it? Yeah, we can just probably divide this by the distance. So here, let's put that in brackets, divided by distance. And that should result in a vector that is normalized. That means it has a length of 1. I hope. Is that even the case? I think that is the case. So that is the force Ax and Ay, and then we have to maybe something's not really precise here. So we calculate a distance, then we calculate the vector And this is, what kind of vector is that? That is the normalized distance vector. It's just the direction vector in which the force is going to be pulling. But then we apply gravity to that force. So this is going to be normalized distance x, normalized distance y. Then we apply gravity. And then what's going to happen is we're going to create gravity. Yeah, we're going to create gravity directional components, and these are AX. AX is a gravity, but multiplied by the direction x normal vector, and then a y, and that is going to be a gravity multiplied by n dy. Let's see. Yeah, let's just try it. I have no idea what's going on then. Oh, that's definitely wrong. So what's wrong here? Circle Vx plus. I think one problem is that we always increment the velocity. Maybe we should start with a very, very low velocity and just see how the circles below behave. So 200, 200, that is the radius and that is the velocity. Let's set the velocity to 0 and this one as well, and that one as well, and that one as well. So now the initial velocities of the two bodies are 0, so I would assume they move toward each other. But they don't. So something must be wrong. We are updating the speed components, yes. But why is the speed not updating then? New position x depends on speed multiplied by delta t, that's fine. Distance n dx. Well, that's all fine, I would say. Maybe the problem is that due to floating point calculations, the values are too small right now to be significant in any way. Yeah, we have to check that. So let's try to increment the gravitational pull a bit and make it 100. And let's see how that looks like. And as you can see, the balls are moving. At least one is moving. Okay, it's just one moving. Just one of them is moving because we're just updating the x and y of one of those two circles. Oh, okay, that's interesting. Okay, so we have to update both circles. Both circles x and y coordinates. And now both should be moving towards each other. Which is also, which is happening. I'm thinking, should we, whoa, what the hell? One of those two balls just shot away. Okay, should we implement masses? Should we implement masses? Yeah, we already have introduced that structure, that field in the structures. I completely forgot about that. And then depending on the mass, maybe we can calculate the gravitational force. So one circle does not pull on itself. The gravity applied to circle 1 depends on the second circle's mass. Yeah, and the gravity on circle 2 depends on the first circle's mass. So let's just do that. Multiply the acceleration by the mass. That's not real physics here. Maybe should we do it properly? So the acceleration is a constant. Then the force is acceleration divided by mass. Or is it multiplied by mass? Newton's first law. Whatever. F is... it's multiplied. Yeah, of course. So the force is mass multiplied by A. But that doesn't really matter. It does not really matter. Wait. Gravity to body force or acceleration. Yeah. Okay. Okay, it was okay. The physics I just invented were correct. Great. So we can just multiply the acceleration applied on the first circle divided we can multiply the acceleration applied on the first circle with the mass of the second circle. So circle 2 mass. Just like that. We can do the same with the y coordinate. And then let's do the same for the other circle, but here, oops, let's delete that 2. Okay, so the second circle pulls on the first circle and the first circle pulls on the second circle. Let's see what happens now. I bet something odd is going to happen because we haven't set the mass of those circles yet. Yeah, it's probably 0, so nothing is happening. So let's just go down to the simulation loop where the masses are set. Let me just set the mass to 1000 for one of the circles, for the big one, and to 500 for the other one, the smaller one. Technically, actually, we could make the mass dependent on the radius. Would be very simple, but yeah. That was not what I expected. Let's reduce the mass a bit and see what happens now. Why is one of the bodies shooting off the screen? It shouldn't happen, or my vision is impaired. So let's try to get the circles move past each other. So circle number 1 is going to move in X direction. Oops. Circle number 1 is going to move in X direction. That is going to be this constant here. And circle number 2 is going to in the opposite direction, but negatively. Oh, it's working. It's working. That's awesome. That's really cool. Holy cow. But why is it going off the screen? Oh, I like that. Why not? It's working well. Maybe I will just reduce the radius because it's too big. Let's make it 10 and maybe 8. So we have two smaller bodies. Yes. And as we can see, they travel in space, they orbit each other. That's awesome. Actually, it looks really, really cool. And yeah, one of the bodies is heavier than the other, so that's the way. So that's the explanation for the look of the simulation. I'm just going to adapt the sizes a bit. I don't really like that they are going off the screen here. But, well, it's a simulation, and apparently those two bodies are going to move off the screen. Yeah, that's it. I just want to make this look good. Make it look a bit better. So let's try this. Let's make the background a bit darker. See, for example, 0x, 1b, 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 1b. And that's not really darker, but it's good. That's really cool. And what if we add trajectories now? And I still have the code for that in the last, in the old project. Should I just copy it over? That would make everything look very, very cool, probably. I will just create a new Vim pane. Let's go over to our other project where we also created trajectories. Let me just... no, I can do it all in one Vim pane. So here I will open a new tab. Let's go over to the other project, Bouncy. It's very similar. And here we have defined those two constants, the trajectory. So what I'm going to do is, or what I want to do is, I would like to trace the path that both bodies are moving. Yeah, I just want to trace the path, and that would look very, 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 very cool. So we have already coded that in one of the last videos. So if you want to find out how that works, please go to that. It was the bouncy ball simulation. So just type bouncy ball simulation in C on my channel and you will find it. And yeah, so that's the code here, fill trajectory. So let me just copy that down here. And then there was update trajectory, and that is part of the code. So this is going to be really a mess of a code right now, but I just care about the results right now. Oops. And I just want to see how it looks like. Actually, the code we just produced is our final product, but I want to see how it looks like if we just do some more graphics. And that's really the cool part. Something that gives this, it gives it the last spark of, well, looking interesting. So let me copy the update trajectory method as well. That is basically a method that tracks where the balls are going and stores the path of the objects in an array. And actually that should be it. Oh no, there's also fill trajectory, which is a simple method that redraws circles based on where they have been before, and where they have been before is something we store in the trajectory object here. So trajectory is just an array of circles, and we store the where has every circle been in the past. Yeah, and we're just drawing that. So is there any error anywhere? Looks fine so far. There's an error in fill trajectory. Ah yeah, of course, I have forgot to copy the declaration of the trajectory. Where is it? There it is. So this is really trashy code right now, but I think it's a cool and exciting project. So let's see how it looks like right now. As you can see, one of the objects is being traced, but it looks a bit weird. Looks like a certain type of cell. So let me make this trajectory a bit better looking. For example, by changing the color. Hex color picker. We're going to pick some light blue. Yeah, maybe a bit darker, like that one. And we're going to set the trajectory color to that. Let's see how that looks like. That's good. Well, then we're going to increase the length of the trajectory. So that makes the trajectory longer. That's cool. Maybe we can make it even longer than that. Then I would like to make the trajectory a bit thinner. For example, 3 pixels. And we are also going to draw the trajectory before drawing the circle. So it's going to be drawn, well, behind the circle. Yeah, looks cool. Looks really cool. And then I'm going to draw also the trajectory of the second circle. So we're going to introduce a new trajectory 2. Trajectory 2 where we're just going to copy this first trajectory. Let's call it trajectory 2. And then we can draw it here. And of course, we also have to update it. I think that should be it. Let's have a look. No, that's not it. We have to pass circle 2 here as well. To be this is passing the state of the circle 2 into trajectory 2 so that it's being stored and later drawn. So let's have a look. Yes. So that's really nice. Oh, but there's a bug. There's a bug in there. There's a big bug. What is that? We are drawing trajectory 2 and circle 2. Oh no, that's getting interesting. So this is trajectory 1. This is trajectory 2. So they are completely separate. This is circle 1. Trajectory 2, circle 2. The index. This is an index tracking how many elements there are in the trajectory right now. But it should be the same for both trajectories all the time, so there can't be the issue. Trajectory 2 length. Trajectory 2. Let's have a look at fill trajectory. And maybe let's have another look at the running simulation. Yeah, something is wrong there. It looks like some array access is not properly done. And that's probably, yeah, we can already see this error right here, stack smashing detected. So what is that? We have to find out where that is coming from. Icon trajectory index. Wait, let's make, just for better looks, let's just make the trajectory thinner, for example 2 pixels, and let's keep it a constant width. I think that might look better in this case. Yeah, that looks cool. And there's the graphic bug. And it looks like some array index is wrong. Quite surely some array index access or something like that is wrong. But I haven't seen it yet. If you know it, then please write it in the comments. Full circle, step, fill trajectory. Before we check that, let's just, let's focus on that. Trajectory, circle, trajectory 2, circle 2. But where is the stack smashing? Let me recompile that with the debug flags active. So how do we do that? GDB, C compile debug. Yeah, we have to add -G. So that is the compiled executable. There's an error somewhere. And we're going to check the application in GDB. So let's call GDB gravity. Oh, what's going on? And let's just do run and see what happens. No, there's no error. How can I find out where the stack smashing is coming from? So, well, how to find out stack smashing? C. I will add this compilation option right here. No stack protector. Quit. Let's exit this. Quit. Let's see. Because I want to see the real error that is being masked by the stack smashing. Fail, come on. Looks different this time. No stack protector. Let's run GDB in Gravity again. Run. I don't really know. Quit. There must be some obvious coding error somewhere. Fill trajectory on the surface, trajectory. This is... So what I'm focusing on right now is that this call refers only to trajectory 1 and circle 1. This is only for trajectory 2 and circle 2. Same here, same there, same. No, this applies to both. This is just circle 1 and trajectory 1, and this is circle 2 and trajectory 2. Let's have a look at how it was done in the other code base here that we coded last time. Here we have the fill trajectory. Then we draw the circle. Then we perform the step. And then we draw... No, then we update the trajectory, which is fine. So maybe there's some coding error that's coming up now. We fill the trajectories here. Color gray? Why do I... Huh? Why is it color gray? Ah, okay. I have to pass the color to the method. Somehow messed that up. Okay, this is now gray. Of course, I don't want it to be gray. So let's fill the trajectory to color trajectory, and color trajectory 2 is going to be a bit different. I'm just picking whatever. This one. 0x. Huh? And that is going to be color trajectory 2. Color trajectory 2. And I'm going to change that here. Color trajectory 2. Okay, now they have different colors. That looks cool. But that still doesn't solve our problem. So it looks like trajectory 2 is the affected trajectory. What happens if we remove the updating for trajectory 1? I'm just trying to figure out if the trajectories somehow interfere with each other. Does the bug still occur? No, now it works. Why? So the creation of trajectory 1, the updating of trajectory 1 destroys the updating of trajectory 2. Let's check what happens if we remove trajectory 2. So that is trajectory 1. That's also working. That means that there's some interference between those two. But how? They don't share a common data structure. Well, trajectory 2. This is trajectory 2. This is trajectory 1. The index of that is currently accessed should be the same for both. This is probably not the issue, right? This is just a local variable. Is there some overflow of one trajectory into the other? We just want to... No, wait. Update trajectory. Where's the code for that? This is the code. There, maybe the error is in here. So we go up to the current. No, what do we even do here? What do we even do here? We copy the trajectory into a temporary shifted copy. This is bullshit code. Starting at index 1. And we move up to the current index, or one before the current index. And this right here is referring to the last index then. And then we starting from index 1, maybe up to equals current index. No, this is probably not it. This is not correct. Yeah, the bug is still there. Trajectory shifted copy is written into the trajectory. And the trajectory is accessed at the current index and is set to circle. We can remove that and call this in any case. I'm just trying to polish the code a bit, because polished code is sometimes easier to troubleshoot. Why is it losing the trajectory? I don't get it. Does that happen with short trajectories as well? Let's just try a trajectory of 50. Yeah, happens as well. Let's try with 5. We probably won't see that one. Yeah, we don't see it. 40. The second trajectory just vanishes. maybe all this indexing of the trajectory and checking the current index is not good. If the current index is bigger than or equal to the trajectory length. Let me remove that. Let me also remove that. We're going to simplify this a bit. So we just assume that the trajectory is always filled, completely filled. So we're shifting the trajectory a bit we're shifting each element in the trajectory to this spot before that, the index before that. Then we write every index. Oh, come on. Into the original array. And then we write the last index into the original trajectory. Maybe because this is maybe this was the error. Maybe that. So first of all, each element why does it have to be starting with 1? Each element can... No. Ah, right. Each element up to the trajectory, of the full trajectory size, is going to be written in the copy, but at a different index. That's blah, 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 blah. Why can't we set the trajectory at this index to circle? Circle is undeclared. It's not undeclared. Why is it undeclared? Ah, now it's declared. Okay. So the last index is going to be the trajectory length minus 1. Then the trajectory is completely copied, so we have to use from 0 to length, but smaller than length, so also up to minus 1. Then here, for this one, we start at index 1, because we're going to discard of element at index 0, and write those into the shifted copy. Maybe I minus 1. And then like that. Maybe that. Oops. Okay. Now we have to remove, to get rid of that segmentation fault, we have to remove all the dependencies on the current trajectory index. We're not going to track that. We don't need to track that. We're going to hack around that, and you will see in a minute how. And in the method fill trajectory, we're going to remove the current index like that, And also here we're going to loop over the whole trajectory length. Oops. I think I just called... No, what did I just do? I called GDB gravity. Is it not running? I don't see it. Come on. I'm typing stuff, but it doesn't register in the console. Now it did. Okay, great. Okay, let's try to... Hey, it's not doing anything. Why? Okay, let me kill that pane. I will create a new one. No, not that one. Over here. And let me compile this again. Okay, current trajectory index is still referenced somewhere. Right there. And here we also need to replace that. And now in update trajectory, there's an error on the structure. What is it? Let me clear that. Too many arguments to function update trajectory. Okay, we can fix that. We pass as input the trajectory, the circle. That's it. But down here we don't. Okay. And then right here also we can remove the index tracking. Now that will result in a segmentation fault, guaranteed. No, doesn't. It doesn't result in a segmentation fault? What? Probably because there's by chance no invalid data in the trajectories. But let's increase the trajectory length. Let's make it 500 again and see how that looks like. And now I'm excited to see whether the bug is still present. No, it seems to be fixed. So there was some, yeah, we probably wrote data into the other array and now the simulation is working fine. So that's a really cool simulation right there. Yes, wow, that's awesome. Have a look at that. They are yeah. Oh my god. Somehow the bouncing of the walls is not really properly working anymore. And now one of the balls is shooting off so far that the other one is not affected by it anymore. Yeah, but that's really interesting. Let's just check the boundary handling. It's in here. Did the ball exit the screen? Ah, of course, just one of the circles is checked for that exit. Let's put that in a new method. That method is going to be called void boundary, maybe screen boundary, step. And we receive as input a structure, circle, pointer, circle. That's going to be enclosed in parentheses. So that is the handling for the screen exit, and then we can handle both circles in here. So both circle and circle 2. Like that. I would expect this to be working now, and I hope this is the last time I call the compile and I open this binary. Let's go. No, there's an error. What's the error? Implicit declaration of function. Screen boundary step. Conflicting types. What's the issue? Conflicting types. Yeah, but what's the conflicting type? Tell me, come on. Implicit declaration of function. Conflicting types for... I know what's going on. Yeah. We're in C and I have to put that method above the call. So up here. Okay. Now I want also to use a bit cooler colors, or not cooler colors, better colors. Let's use some neon green. For one trajectory. And let's use some red for the other one. Yeah, that one. 0x. Let's remove this hashtag thing. Okay. I hope this works now. So, okay, this is the big announcement. Now comes the point in time where everything is being decided. Let's compile and execute this. This is the last time I'm going to press execute and compile in this episode. I'm going to manifest it now. This is the last time. Let's go. There's still some warning. No, this is not the last time apparently. Incompatible pointer type, but somehow it executes perfectly. Passing argument 1 of screen boundary step from incompatible pointer type. Yeah. But how did it handle that? Why is the code even working despite that issue? I was passing a pointer of a pointer. And we don't do that. So this is right now what we want. Did the compiler just auto-fix me calling a pointer of a pointer where actually just a pointer was expected? If yes, nice. Okay, now this is going to be the last time I'm pressing execute. Let's go. There's still a bug. But I removed that. Let me just look for that. Passing argument 1. No, it's fine. It's fine. It's fine. The code is working. Okay, let's go. So this is the final demonstration. Let's just do very long trajectories because this will look very cool in the simulation. Let's do 2000 and just pray that this does not crash my CPU. And let's see how that looks like. Okay. So this is our simulation right there. It's awesome. Let's see what happens at the boundary. Yeah, it's going to collide with the boundary and fall back. Yes. And that's the funny part of what we're doing here. We yeah, if this was real space, then obviously, oh my God, both of those bodies would move off the screen. But in our case, that's not happening because they are accelerating each other all the time and bouncing off the walls. Yeah. This is a bit of a mess. They are accelerating a bit too much. But this is not an issue with the code itself, but with the parameters that the simulation is running in. First of all, the boundary checks and the gravitational force factor probably. Also, it's a problem that both bodies can just pass through each other. So let's do another one. Let's make them move a bit slower, for example 5 and -5. And let's make one move up slowly and the other move down slowly. And let's just reduce the gravitational force factor here a bit and make it 10 instead of 100, and let's see how that looks like. Yeah, that looks calm. Too calm, so now they don't affect each other anymore. Yeah, when both bodies get too close to each other, they are at that distance is approximating 0, so the gravitational pull between those two is approximating infinity. So that's not a really good parameter here. Let's just leave it at that. At this. Oh, no. Yeah. I will change those back to 0 again. Let's compile. No, they shouldn't move toward each other that much. Maybe that's because they're too slow now. So let's do 15 minus 15. Let's see. Yeah, that's too fast, so they just go past each other. Yeah, probably the 10 was fine, the 10 that we had earlier. Maybe the distance between both bodies can be incremented a bit. Let's see how that looks like. Yep, that's a nice big orbit. And a small bounce off the wall, which wouldn't happen in space. It's just interesting to see these nonlinear trajectories, in my opinion. And now there's an infinite acceleration due to a distance approximating 0. Yeah. Okay, I think for a proper simulation, we have to remove the boundary check. It's just not going to happen in space in a situation where there's no gravity, there's no boundary. So let's have a look at that. And maybe we should also add collision detection in the future. But this is our simulation now. This right there is the best result we can get now. And in just a few orbits, both planets are going to move off the screen. And then they live happily ever after. That's our orbit simulation. I hope you enjoyed it. And if you did, then please leave a like, follow, subscribe, and let me know everything in the comments that I did wrong. I think I'm going to use that as a screenshot. That looks really cool. It's awesome. Okay, bye-bye.